the different types of transportation models used in transportation plan, the formulas and the principles behind those models. Now, let's have a few samples of these models, starting with our first stage, which is the trip generation. So, trip generation is the first stage of the classical first generation aggregate demand models. The trip generation aims at predicting the total number of trips generated and attracted to each zone of the study area, as what I have discussed previously in our other topics. In other words, this stage old and socioeconomic attributes. In this section, basically, we will be familiarizing two main modeling approaches. So those two are growth factor modeling and the regression modeling. So let's start first with the growth factor modeling. So growth factor modes tries to predict the number of trips produced or attracted by a household or zone as a linear function of explanatory variables. The models have the following basic equation. So it's the T's of I, capital T, is equivalent to the F's of I and the T's of I, small letter t, where your T's of I is the number of future trips in the zone, and T's of I, or your small t's of I, is the number of current trips in the zone, and your F's of I is a growth factor. So the growth factor Fi actually depends on the explanatory variables such as the population of the zone, average household incomes, average vehicle ownerships. So for the population, it is denoted as P, for the average household income as I, and V for the vehicle ownership. So it creates this formula. Your F sub I is actually equal to P sub I raised to D times I sub I raised to D plus V sub I raised to D all over P sub I raised to C times I sub I raised to C times the V sub I raised to C, where the subscript D actually denotes the design year and the subscript C denotes the current year. So let's have an example for this one. So car and the average trip generation rates for each group is respectively 5 and 2.5 trips per day. Assuming that in the future, all household will have a car and the growth factor and future trips from that zone if the population and income remains constant. So let's try to solve this one. So we have first the current trip rate T sub I. So that is actually equal times the 5 trips per day. So we actually have 2,062.5 trips per day. Next, let's solve for the growth factor f of I, which is equal to v sub I raised to d over v sub I raised to c, equivalent to 550 all over 275. So again, D denotes for the designed year and C for the current year. So combining both, we will actually have a growth factor of 2. Next, let's solve for the number of future trips, your T sub I, which is of I equivalent to 2 times 2,062.5, we have an answer of 4,125 trips per day. So the trip rate in the future, you can see. Therefore, the number of trips in the future will be 550 households, 5 trips per day, which is equivalent to 2,750 trips per day. So it may be denoted from this example that the actual trips generated is much lower than the growth factor method. Therefore, the growth factor methods are normally used in the prediction of external trips where no other methods are available. But for internal trips, regression methods are more suitable and will be discussed next. So what is that regression method? X of 3, so on and so forth. Where your X sub i's are prediction factor or explanatory variable. The most common form of trip generation model is a linear function of the form, while your T sub I is equivalent to a sub 0 plus a sub 1 x sub 1 plus a sub 2 x sub 2 plus a sub I, so on and so forth. Where a sub i's are the coefficient are example. Let the trip rate of a zone is explained by the household size done from. It was found that the household size are 1, 2, 3, and 4. The trip rate of the corresponding household is as shown in the table below. So this one is fit a linear equation relating trip rate and the household size. So we're going to create a linear equation. So in this case, if you can see, this is our x, this is our y. So this one is the summation of our y. So now let's solve for that one. So the linear equation will have the form, again, linear equation is equal to y is equal to b sub x plus a, where y is the trip rate and x is the household size, while your a and b are the coefficients. For a best fit, b is given by this one. So your b is equal to n summation of x times y minus the summation of x times the summation of y all over n times the summation of x squared minus summation of x quantity squared. Meanwhile, your a is just equal to y uh, y mean minus b times x mean. So the summation of x is equal to 3 times 1 plus 3 times 2 plus 3 times 3 plus 4 times 4. So we have the summation of our x, which is equivalent to 30. While the summation of x squared is equivalent to 3 quantity squared plus 3 times 2 quantity squared plus 3 times 3 squared plus 3 times 4 squared. While the answer for this one is equivalent to 90. Moving forward, now let's solve for the summation of y, which is equivalent to 5 plus 9 plus 12 plus 17, which is equivalent to 43. While your summation of x times y is equal to 1 times 1 plus 1 times 2. If you can see, this is just about this table. So on and so forth. So the answer for your summation x times y is equivalent to 127. Now let's get your y mean. Is equivalent to 43 over 12. That is equivalent to 3.58. For your x, we have 30 over 12. Now we have an answer 2.5. So we're getting close for the equation. So again, our b. Now we have the values for this one. Let's just substitute. So we have 12 times 127 minus 30 times 43 all over 12 times 90 minus 30 squared. So we have a value of 1.3. Now let's solve for the value of your a, which is equal to y mean minus b times x mean. So that is 3.58 minus 1.3 times 2.5. That is equivalent to 0.33. Substituting in our linear equation, we should have y mean is equal to 1.3x minus 0.33. So that is our linear equation. Okay, so now we are in our trip distribution. So here, the decision to travel for a given purpose. So the decision to travel for a given purpose is called trip distribution. So this generated trips from each zone is then distributed to all other zones based on the choice of destination. This is called trip distribution, which forms the second stage of travel demand modeling. There are a number of methods to distribute trips among destinations, and two such methods are growth factor modeling and gravity model. Growth factor model is a method which responds only to relative growth rates at origins and destinations, and this is suitable for short-term trend extrapolation. interpolation. In gravity model, we start from assumptions about trip making behavior and the way it is influenced by external factors. An important aspect of the use of gravity models is their calibration. That is the task of fixing their parameters so that the base year travel pattern is well represented by the model. So let's start with your uniform growth method. So here, advantages are that they are simple to understand and they are useful for short-term planning. The limitations for this one is that the same growth factor is assumed for all zones as well as attractions. Oh, anyway, if the only information available is about a general growth rate for the whole of the study area, then we can only assume that it will apply to each cell in the matrix. That is a uniform growth rate. The equation can be written as T sub ij is equivalent to F times T small t is the previous total number of trips, while your capital T sub ij is the expanded total number of trips. Let's have an example to further understand. 78 respectively. If the growth factor is 1.3 and the cost matrix is as shown below, find the expanded origin constraint growth trip table. So we have this table from zones 1, 2, and 3 which is equivalent to 1.3. Therefore, multiplying the growth factor with each of the cells in the matrix gives the solution as shown below, which is this one. So we just multiplied 1.3 for each um, cells in our matrix. So that's the number of trips based on our growth factor. That is in your uniformly in a uniform growth rate. While the next one, here the error is calculated as E is equivalent to the summation of O sub I minus O sub I raised to 1, the absolute value of that, plus summation D sub j minus D sub j raised to 1, and the absolute value of that one as well, where O sub I corresponds to the actual productions from zone I, and O sub I raised to 1 is the calculated production from that zone. Similarly, D sub j are the accurate attractions from that zone. So to further understand, let's have an example. So the base year trip matrix for a study area consisting of three zones is given. The productions from the zone 1, 2, and 3 for the horizon year is expected to grow to 98. Compute the trip matrix for the horizon year using doubly constrained growth factor modeling model using furnace method. So let's have a solution for that here. 106 plus 122, which gives us 326. So the sum of production in the horizon year, that is emission D sub j, they both are found to be equal. Therefore, we can proceed. The first step is to fix B sub j is equivalent to 1 and find the balancing factor 88 over 78, which is equivalent to 1.26. A sub 2 is equal to 106 over 92, which is equivalent to equal to 1.49. So further, T sub 1 is equal to T sub 1 times A sub 1 is equivalent to 20 times 1.26 is equivalent to 25.2. Similarly, with your T's of 1, 2 is equivalent to T's of 1, 2 times A sub 2 is equivalent to 36 times 1.15, which is equivalent to 41.4. Multiplying, so the matrix will be obtained. So here is the matrix. We already have equal to 25.2 plus 41.4 plus 32.70 is equal to 90 times B sub j. For example, B sub 1, we have 102 all over 99 formula. And then we are going to have an answer of 1.03. For B sub 2, the same thing, so on and so forth. Meanwhile, for our O sub I raised to 1, we have 25.96 plus 35.53 plus 36.69 is equal to 98.18. So the matrix is as this one. B sub j and D sub j are located here. So this is the O sub I. obtaining this matrix, this will be our answer. So therefore, error can be computed as, again, error is when the summation absolute value for that plus the summation of the absolute value of d sub j minus the small d sub j. So summing up everything based on this matrix, an error we have is equivalent to 1.32. Now let's move on to the third stage, which is the modal split. So the third stage in travel demand modeling is the modal split. The trip matrix or OD matrix obtained from the trip distribution is sliced into a number of matrices representing each mode. First, the significance and factors affecting mode choice problem will be discussed. Then a brief discussion on classification of mode choice will be made. Two types of mode choice models will be discussed in detail: binary mode choice and the multinomial mode choice. So in the next slides, we will be discussing future topics about the mode choice problem. So let's start with the binary logit model. So binary logit model is the simplest form of mode choice where the travel choice between two modes is made. The traveler will associate some value for the utility of each mode. If the utility of one mode is higher than the other, then that mode is chosen. But in transportation, we have this utility also. So what is that? So this utility here is the travel cost. This can be represented as this equation. So you are also given here what are the values of this one, what's the use of this one. So binary logit model we have here. If c of I sub j raised to 2 minus c sub I j raised to 1 is positive, then mode 1 is chosen. Number 2, if c sub ij squared minus c sub ij raised to 1 is a negative, then mode 2 is chosen. But if c sub I sub j raised to 2 minus c sub ij raised to 1 is equivalent to 0, then both modes have equal probability. So this relationship is normally expressed by a logit curve as shown in figure 9 is to 1. I'll show that one later. Therefore, the proportion trips by mode 1 is given by this equation. You also have the values for that one. So let's go to the graph. I mean the figure 9 is to 1, the logit function, this one. It's being graphed. So the example here is that the number of trips from zone I to zone J is 5,000 and two modes are available which has the characteristics given in table 9 is to 1. Compute the trips made by mode bus and the fare that is collected from the mode bus. If the fare of the bus is reduced to 6, then find the fare collected. So we have two options here, two modes, by car and by bus. So we have this data based on the trip characteristics, and we have this logit function. So solution. So the cost of travel by car, let's have car equation. So we have C cost of in car, we have 0.03 times 20 plus 18 times 0.06 plus 4 times 0.1, which is equivalent to 2.8. While for the cost of travel by bus, we have come up to an answer of 2.18. So the probability of choosing mode car, we have this equation. When we got an answer of 0.52, while the probability of choosing mode bus, we have the answer 0.475. So the binary logic model is this one. We have this, the cost, and we have the probability. So the trip characteristics we have right now is this one. So the proportion of trips by car is this one. 5,000 times 0.52, we have 2,600. the proportion of trips, sorry, the proportion of trips by bus, we have 5,000 times 0.475, which is 2,400. And the fare collected from the bus is equivalent to 2,400 times 9 is equivalent to 21,600. Next function. Cost function of the bus gives us an answer of 1.88. While the probability of choosing mode as a bus as our mode, we have an answer of 0.55. While the proportion of trips by bus, we have an answer of 2,750 from 5,000 times 0.55. And the fare collected from the bus, 100. So the results are tabulated. Now let's move on to the multinomial logit model. So we have this equation, try to compare it with the binary models involved. So let's have an example. So let the number of trips from I to J is 5,000 and three modes are available, which has the characteristics given in this table. So compute the trips made by three modes and the fare required to travel by each mode. So we have the car, the bus, and the train. So those are our available modes. And here are the given data. So same thing, you compute. We have to compute the cost of travel by car, by bus, and by train, which gives us the answers 2.8, 1.88, and 1. While after computing the cost of travel for the different modes, let's compute the probability of each mode. This one's by car, and the other one is by bus. We get these answers. I think I forgot to include the train. I think I left that one. So we have the trip characteristics. So again, first let's compute the probability. Oh, here's the train. I thought I left it on the other slide. So we have this one. Next, we have the proportion of trips by car was on 552.5. So similarly, proportion of trips by train, we get to have 5,000 times 0.5657, which is going to 2,828.5. So we can put all this in the form of shown in the previous table. Now the for assignment. So the process of allocating given set of trip interchanges to the specified transportation system is usually referred to as traffic assignment. The fundamental aim of the traffic assessors are number one, to estimate the volume of traffic on the links of the network, obtain origin to destination or your OD pair, and lastly, to identify congested links and to collect traffic data useful for the design of future junctions. So we have an sample of an all or nothing assignment. So in this method, the trips from any origin zone to any destination zone are loaded onto a single minimum cost or the pathway between them. As what I've told you before, we are actually using this now. Which way has lesser traffic, which way is cheaper, which mode is cheaper. So it's the same thing. It's the same thought. It's the same process as what I have discussed from the previous definition of a trip assignment. So let's just proceed with the example. So to demonstrate how this assignment works, an example network is considered. This network has two nodes, having two paths are as links. So let us suppose a case where travel time is not a function of flow as shown. In other words, it is constant as shown in this figure. So we have two link problem with constant travel time function. So 10 and a 15. So the travel time function for both the length is given by t sub 1 is to 10 and t sub 2 is equal to 15. And the total flows from 1 to 2 is given by q sub 12, which is equivalent to 12. Since the shortest path is link 1, all flows are assigned to it, making x of 1 equivalent to 12 and x of 2 is equivalent to 0. So that ends my example.